6.5 is limits of indeterminate forms. L'Hôpital's rule. I know this looks like L'Hospital's rule, but it's actually pronounced L'Hôpital's rule. Okay. And you can look up, this was the guy that came up with it, L'Hôpital. So you can look him up and read about him. Your essential question is, how do you use L'Hôpital's rule to evaluate limits of the indeterminate form? So if you remember, this is a review. Indeterminate form we have many different forms that become indeterminate forms. So like if I end up with 0 over 0, if I end up with infinity over infinity, maybe I end up with 1 to the infinity power, maybe I end up with 0 to the 0 power, or maybe infinity to the 0 power. All of these take on the indeterminate form, meaning that they don't have a value. So if that happens, there is this thing called the L'Hôpital's rule that uses calculus to help you evaluate it. So to find the limit of an indeterminate form, use L'Hôpital's rule. Okay, so what is L'Hôpital's rule? Well, it's really simple actually. Compared to some of the stuff we've been doing, you're going to really appreciate this. So if you have a function where you have, g of x over h of x, and the limit as x goes to some number c of g of x is the same as the limit as x goes to c of h of x. Oops. And let's just say that those both equal 0. So basically you get an indeterminate form of 0 over 0. This would also be true if that happens with, infinity over infinity. Okay. Then the limit as x approaches some number c of f of x will equal the limit as x approaches c of the derivative of the numerator and the denominator separately. You don't even have to do the quotient rule, provided the latter limit exists. Okay, so this is true basically for all of these indeterminate forms. If you end up, trying to take the limit of a function that looks like this, and you end up where you get one of these indeterminate forms, you can use L'Hôpital's rule. You just basically take the derivative of the numerator and the denominator, and as long as that limit exists, then you're golden. If it doesn't, you could try L'Hôpital's rule a second time, or even a third time, and see if it works. Okay? So this would be true even when x maybe isn't approaching a value, but also maybe when it's approaching infinity, for example. So I'll put a little note in there. So let's do one of these. Okay, we are going to find the limit L as x goes to 1 of x squared plus 2x minus 3 all over ln of x. So the first thing I want to do is I want to see if I can actually evaluate this. So I plug 1 in. I get 1 plus 2. So that's 3 minus 3. So I end up with 0 in the numerator. And then the ln of 1 is also 0. So I end up with an indeterminate form, right? This right here. This is one of our indeterminate forms. So what I'm going to do now is I'm going to use L'Hôpital's rule. So this will actually equal the limit as x goes to 1. Now I'm going to take the derivative of the numerator. And so when I do that, I get 2x plus 2. And nothing here, that's a constant. And then the derivative of the bottom is 1 over x. So now I can plug 1 in. When I plug 1 in here, let's see, that's 2 plus 2 is 4. Over 1 divided by 1 is 1. So you end up with 4. Pretty easy stuff, right? You're probably saying to yourself, why didn't we just start doing this from the very beginning? All right, let's try another one. Let's see. Yeah. We'll call this one example 2. The directions will be to evaluate, and I'll do 2 of these. So the first one will be the limit as x goes to infinity of x squared times e to the negative x. Well, to help me out, I might rewrite this so that I basically have a numerator and denominator. So I can say that this is also the limit as x goes to infinity of x squared over e to the x. Well, the limit as x goes to infinity of x squared, right, here I'm just going to think about their graphs. X squared, that's going to go on forever, so it's going to reach infinity, or head towards infinity, not reach it. It can't reach infinity. And then the same thing with e to the x, that's an exponential function, and so as I head towards infinity on the x-axis, my output will also head towards infinity. So once again, I have an indeterminate form. So I'm going to use L'Hopital's rule. All right, so I'm going to continue on the limit as x continues to infinity. Let's see, this will give me 2x over, well, the derivative of e to the x is e to the x. So let's see, that's going to give me, well, once again, I got infinity over infinity. So that's not going to work. I still have an indeterminate form. So now what am I going to do? Well, what I'm going to do now is I'm going to use L'Hopital's rule. A second time. And I'll use it on what I have here. So the limit as x goes to infinity, now that's going to give me 2 over still e to the x. The derivative of e to the x is always going to be e to the x. So really what this is this is 2 over infinity. And this is something that we talked about quite a while ago, but if you recall that the limit as x goes to infinity of 1 over x, or any constant over x, basically that denominator is going to get really, really big as the numerator stays the same. So this thing goes to 0, which will be true here as well, right? So this equals 0. All right, let's try another one. That's A, let's do B. So we'll do the limit as x goes to 1 of x to the 1 over 1 minus x power. So going in and trying to evaluate this, I'm going to have plug 1 in here. I get 1 raised to the 1 over, well, 1 minus 1 is 0. So as this goes to 0, this whole thing is going to infinity. So this becomes 1 to the infinity power, which is really an indeterminate form. Okay, so what I'm going to do now is I'm going to use L'Hopital's rule. The problem is this looks pretty ugly and it's not really in any form for me to use L'Hopital's rule. So I need to get it into a form that will allow that to happen. So really I needed to have a numerator and a denominator. So in order to do that, I'm going to use logarithmic differentiation. I am going to let L equal the limit as x goes to 1 of x to the 1 over 1 minus x power. So now I'll take the ln of both sides. So the ln of L equals, I'm going to keep the limit out front, the ln of this side. So using that logarithm now allows me to bring down my power. Simplifying that, I should see that now I've got it in the correct form. So the ln of L will equal, let's see, the limit as x goes to 1 of ln of x over 1 minus x. Now I've got it in an appropriate form where I can do L'Hopital's rule. Before I do that, though, let me just go ahead and double check that it still doesn't work out. So if I plug 1 in here, I'm going to get 0. I plug 1 in there, I get 0. So this still gives me 0 over 0. Okay. So continuing on, I'm going to have the ln of L will equal, okay, so the derivative of the numerator, oh, sorry, this will be the limit as x goes to 1. The derivative of the numerator will be 1 over x. The derivative of the denominator, well, that becomes 0. And the derivative of negative x is just negative 1. So let's see what this ends up giving us here. Oh, what happened to my ln? I lost. Oh, no, I still have that. That's good. So I'm going to have the ln of L equaling, let's see, 1 over 1, right? As I plug 1 in there, it's going to give me negative 1. All right, well, now how do I get L here by itself? One way to do that is to raise or to give each side a base of e. Another way would be to rewrite this using exponential form. So I can say, all right, I know that there's a base e here. So this is really e to the negative 1 equals L. And then you can plug that into your calculator. So L will be approximately, if you plug that in your calculator, you get 0.36788. How about that? And there you go.